23rd of July 1943, 11:34 hours. Kummersdorf Proving Grounds, 30 kilometers south of Berlin. The morning fog had burned off the test track an hour ago, leaving the summer air thick and still. Hauptmann Ernst Bauer stepped out of the technical evaluation office, clipboard in hand, and walked toward the captured American tank sitting in the center of the proving ground. At 38, Bauer had spent 15 years as an automotive engineer before the war, first at Auto Union, then at Daimler-Benz. For the past 18 months he'd commanded the Foreign Equipment Evaluation Section at Kummersdorf, examining every piece of Allied armor German forces managed to capture intact. The M4A1 Sherman had arrived 3 days earlier from Tunisia, captured during the fighting at Kasserine Pass. Bauer had already reviewed the preliminary reports: 75mm gun, 30-ton weight, 350 horsepower Continental radial engine, standard American construction. The external examination yesterday had confirmed the intelligence assessments: welded hull, cast turret, relatively thin armor by German standards. Nothing surprising. But this morning's assignment was different. Today they would tear it down to the transmission. Bauer's team of 6 mechanics and engineers stood waiting beside the Sherman, tools already laid out on canvas tarps. They'd performed this ritual dozens of times before, captured T-34s, British Matildas, Crusaders, even a few early Valentines. Each examination followed the same pattern: photograph, measure, document, compare against German equivalents, identify weaknesses, file report. Herr Hauptmann, Oberfeldwebel Klaus Richter called out, gesturing toward the Sherman's engine deck. "We've already removed the access panels. Ready when you are." Bauer nodded and climbed onto the rear of the tank. The Continental engine sat exposed, its radial configuration immediately familiar, essentially an aircraft engine adapted for ground use. Crude, he thought, but typically American. Take what's available, make it work, move on to production. What he couldn't see yet, what none of them could anticipate, was that the next 6 hours would fundamentally alter their understanding of American industrial capability. The transmission assembly waiting beneath that engine would reveal a truth more devastating than any battlefield defeat. The Americans had solved engineering problems that German factories, with all their precision and craftsmanship, had never managed to overcome. This single component would explain why American tanks were appearing in ever greater numbers across 3 continents, while German production facilities struggled to maintain even minimal output. The arithmetic of industrial war was about to become painfully, undeniably clear. Bauer directed his team to begin the engine removal. Standard procedure: disconnect fuel lines, electrical connections, cooling system, exhaust. 2 mechanics worked the overhead hoist into position, while Richter and another engineer loosened the mounting bolts. 90 minutes later, the Continental engine swung free, revealing the transmission assembly beneath. "Mein Gott," Richter muttered. The transmission housing was a single cast aluminum unit, roughly 60 centimeters wide and 40 centimeters deep. But what stopped Bauer mid-reach for his measuring calipers was the complete absence of external oil lines. No flexible hoses, no connection points for auxiliary cooling, no external filter housing. "They've integrated everything," Bauer said, more to himself than his team. He ran his hand along the housing surface. The casting quality was exceptional. Smooth, uniform wall thickness, no visible porosity or surface defects. The mounting flange showed precision machining with tolerances he estimated at less than 0.1 millimeters. "Get the German ZF transmission manual," Bauer ordered. The AK-7200 from the Panzer. While a mechanic retrieved the technical documentation, Bauer's team began measuring the Sherman's transmission assembly. The numbers accumulated on his clipboard: overall weight 112 kilograms, number of external connection points 4, 2 drive shafts, 1 shift linkage, 1 drain plug. Visible fasteners, 28 bolts, all the same size. Separate components requiring installation. 0 Richter returned with the Panther transmission specifications. Bauer laid the documents side by side. The German ZF AK-7200, weight 178 kilograms, external connection points 14, including oil cooling system. Visible fasteners, 63 bolts in 8 different sizes. Separate components requiring installation. 7, External oil pump, cooler, filters, lines. They've made it 66 kilograms lighter, Bauer said slowly, and reduced the installation complexity by, he counted again, at least 70%. Perhaps they've sacrificed durability, one of the younger engineers suggested. Lighter materials, simpler design. It cannot be as robust. Bauer wanted to believe that. The standard German engineering assumption, American mass production meant lower quality, acceptable only because they could replace equipment quickly. Quantity over quality. Let's open it, he said. The team removed the 28 identical bolts. Bauer noted they were all standard 12 mm interchangeable, unlike the mixture of metric sizes on German equipment. The aluminum housing separated cleanly, revealing the gear assembly inside. What they saw made no sense. The gear teeth showed virtually no wear. Bauer had examined transmissions from Panzers with 500 kilometers of use showing significant tooth surface damage. This Sherman, according to the capture report, had been in combat operations for 3 months and had traveled an estimated 1,200 kilometers across North African terrain. The gear teeth looked nearly new. Check the bearing surfaces, Bauer instructed. The mechanics carefully extracted the main shaft assembly. The roller bearings showed the faint discoloration of normal heat cycling, but no scoring, no pitting, no metal fatigue. The oil drained from the housing was clean, with minimal metal particulate. Richter held up the oil filter element, a simple pleated paper design integrated into the bottom of the housing. It's barely dirty, he said, after 1,200 kilometers. Bauer turned to his notes from the last Panzer IV transmission failure analysis, conducted just 3 weeks earlier. That transmission had failed at 430 kilometers, requiring complete replacement. The failure analysis had documented excessive bearing wear, gear tooth fracture, and oil contamination from metal particles. What's the recommended service interval? Someone asked. Bauer found the captured American technical manual in the documentation pile. He flipped to the maintenance schedule section. Transmission oil change every 1,600 kilometers, he read aloud. Transmission rebuild every 8,000 kilometers or as needed. The proving ground fell silent except for the distant sound of another test vehicle on a far track. 8,000 kilometers. The German ZF transmissions in Panther tanks were experiencing failure rates of 30–40% before reaching 1,000 kilometers. The Tiger's Maybach transmission was considered exceptional if it lasted 1,500 kilometers between rebuilds. The Americans had specified an 8,000-kilometer service interval, and this particular transmission, after 1,200 kilometers of combat use, showed almost no wear. Maybe this one is exceptional, the young engineer offered. An outlier. Better manufacturing on this particular unit. Bauer hoped he was right, but he'd been doing this work long enough to recognize a pattern when he saw one. Send for any other Sherman transmissions in storage, he ordered, and request priority access to any future captures. We need more data. Over the next 2 weeks, 3 more Sherman transmissions arrived at Kummersdorf. One from a tank destroyed in Sicily, its transmission intact despite the vehicle's fire damage. 2 more from tanks captured in Italy during the Allied landings. Bauer's team performed identical examinations on each unit. The first Italian transmission, from a tank with an estimated 800 kilometers of use, showed the same minimal wear pattern. Clean oil, minimal bearing damage, gear teeth in excellent condition. The second, with approximately 1,400 kilometers, was nearly identical. Even the fire-damaged unit from Sicily, despite external heat damage to the housing, had internal components in serviceable condition. It's not an outlier, Richter said quietly. They're all like this. Bauer nodded, making notes. But he was searching for the inevitable compromise. American production was quantity-focused, everyone knew this. Simplified designs, lower-grade materials, acceptable reliability, because replacement parts were abundant. There had to be a weakness. Let's examine the gear metallurgy, he instructed. They sectioned gear teeth from 2 of the transmissions and sent samples to the Kummersdorf Metallurgical Laboratory. The results arrived 3 days later. Steel alloy composition. Carbon steel with nickel-chromium molybdenum alloying, case hardened to Rockwell C-scale 58–62 on surface, with core hardness of RC 30–35. Heat treatment showed uniform depth of 1.8–2.2 millimeters. Bauer compared it against the specifications for German tank transmission gears. The American material was equivalent in quality, and the case-hardening depth was actually superior. German gears typically achieved 1.2–1.5 millimeters of hardening depth. They haven't compromised on materials, he said. If anything, the heat treatment is more robust than ours. The young engineer who'd suggested sacrificed durability 2 weeks earlier remained quiet. Bauer moved to the next system, the synchronized shifting mechanism. He'd noticed during the first examination that the Sherman'S transmission used a synchro-mesh design, a relatively recent innovation that allowed easier gear changes without double clutching. German tank transmissions used either unsynchronized sliding gear systems or, in the latest models, complex servo-assisted designs that required significant additional components. The Panzer's transmission used a hydraulic shift assistance system that added 23 kilograms of weight and required separate maintenance. The Sherman's synchro-mesh system was entirely mechanical, required no additional components, and was integrated into the basic transmission housing. Total weight addition, approximately 3 kilograms. How does it function? Richter asked, examining the brass synchronizer rings. Bauer had already studied the mechanism. Cone clutch design. The brass ring matches rotational speed before the gear engages. Simple, elegant, and he tested the movement manually. It requires minimal force. He'd driven Panther tanks. Shifting required significant effort, even with the hydraulic assistance. A long day of driving left every tank commander with aching arms. Test the shift force requirement, Bauer ordered. The mechanics rigged a spring scale to the shift lever and measured the force needed to change gears. Average force, 8 kilograms. Maximum force, 12 kilograms. Bauer retrieved his notes from Panther evaluations. Shift force without hydraulic assistance, 35 to 40 kilograms. With hydraulic assistance, 18–22 kilograms. The Americans had achieved easier shifting with a simpler system, less weight, and no additional components. What about the final drive? Another engineer asked, pointing to the differential assembly. They examined the differential and final drive gears next. Again, single-piece cast housing, integrated lubrication, minimal external components. The gear ratios showed careful optimization. The Sherman had a top speed of 38 kilometers per hour on roads, with good low-speed torque for cross-country mobility. More importantly, the final drive showed the same minimal wear characteristics as the transmission. After 200 kilometers, the differential gears looked barely used. German final drives, particularly on heavier tanks, were experiencing catastrophic failure rates. The Tiger tank's final drives rarely lasted 500 kilometers before requiring replacement. The Panthers were marginally better, but still problematic. They've designed the entire drivetrain as an integrated system, Bauer said, stepping back to look at the complete powertrain layout on his documentation table. Engine, transmission, final drives, everything optimized to work together. Minimal interfaces, minimal complexity. And it works, Richter added, reliably, in combat conditions. For thousands of kilometers. Bauer had been searching for 2 weeks for the compromise, the weakness, the trade-off that would explain why American tanks could be produced so quickly. He'd found none. Instead, he'd discovered something far more troubling. The Americans had out-engineered German precision with simplicity. Before we continue with what Hauptmann Bauer discovered next, I want to hear from you. What's the most surprising WWII technology you've learned about? Drop a comment below and let me know where you're watching from. And if you're finding this technical analysis fascinating, hit that like button. It helps more history enthusiasts discover these stories. On August 12, 1943, 3 weeks into the Sherman evaluation, a Kummersdorf machinist named Werner Koch approached Bauer with a question that would open an entirely new dimension of the problem. Herr Hauptmann, I've been examining the manufacturing marks on these transmission housings. May I show you something? Koch led Bauer to the workbench where he'd laid out the aluminum housing from the first Sherman. He pointed to barely visible marks inside the casting. These are die markings, Koch explained, from the casting process, and here, he traced his finger along the interior surface. You can see the draft angles and parting lines. This was die cast, not sand cast. Bauer understood the significance immediately. Sand casting was standard for complex shapes. Pour molten metal into a sand mold, let it cool, break away the sand. Simple, flexible, suitable for small production runs. But sand casting produced rough surfaces requiring extensive machining and finishing. Die casting, forcing molten metal under pressure into permanent steel molds, produced much smoother surfaces and tighter tolerances. But die casting required massive, expensive dies that took months to manufacture. The process was economical only for very high production volumes. Die casting something this large, Bauer said slowly, running his hand over the 60-centimeter housing. That's extraordinarily difficult. Koch nodded. The die itself would weigh several tons. The casting pressure required would be enormous. The temperature control, the metal flow, the solidification rate, every variable has to be precisely managed. Bauer knew German industry had attempted die casting for smaller automotive components with mixed success. Mercedes-Benz had experimented with die-cast engine blocks in the 1930s, but abandoned the effort due to quality control problems. The dies cracked under thermal stress. The castings had porosity issues. The dimensional accuracy wasn't sufficient. The largest die casting I've seen in German production is maybe 20 centimeters, Koch continued. Engine brackets, differential covers, small components. This, he gestured at the transmission housing, this is 3 times that size. The engineering required to make this work reliably is extraordinary, Bauer finished. But the implications went further. Die casting wasn't just about the technical achievement of making it work once. It was about making it work thousands of times, producing consistent, high-quality parts in volume. How many of these do you think they can produce? Bauer asked. Koch considered the question. If they've solved the die casting problem at this scale, and if the dies hold up to production use, I'd estimate one complete housing every 15 to 20 minutes, maybe faster if they have multiple die casting machines. Bauer did the mathematics in his head. 20 minutes per unit meant 3 per hour. Running 2 shifts. German factories were increasingly limited to 2 shifts due to labor shortages. That was 48 housings per day. Call it 45, accounting for downtime and maintenance. 45 per day meant 1,950 per month from a single factory line. And machining? Bauer asked. After casting? Minimal, Koch replied. Die casting produces near net shape. You'd need to machine the mounting surfaces, drill the bolt holes, tap the drain plug. Maybe 3 hours of machine time total. Compare that to, he didn't need to finish. German transmission housings were fabricated from multiple steel plates, welded together, with every surface requiring extensive machining. A Panzer transmission housing required approximately 80 hours of combined welding and machining work. 3 hours versus 80 hours, Bauer said quietly. And that's just the housing, Koch added. The Americans are probably using similar high-volume processes for the gears, shafts, everything. They've optimized the entire manufacturing process for speed and volume. Bauer walked to his office and retrieved the intelligence reports on American industrial capacity. He'd read them before but hadn't fully absorbed the implications. Ford's Willow Run plant, projected production of 1 B-24 bomber every 63 minutes. Chrysler's tank arsenal, target production of 1,000 Sherman tanks per month from a single facility. General Motors, converting automobile plants to military production, combined capacity estimated at multiple thousands of vehicles monthly. These weren't goals or propaganda figures. The transmission in front of him proved these were achievable targets. The Americans had solved the engineering problems that made high-volume precision manufacturing possible. German industry, for all its craftsmanship and reputation for quality, had never attempted production at this scale. The entire concept of designing for manufacturability, making parts that were inherently easy to produce in volume, was fundamentally different from the German approach of craft precision. They're not making inferior equipment quickly, Bauer said, more to himself than to Koch. They're making superior equipment quickly, Koch nodded, and we cannot replicate this. Not with our current manufacturing base, not with our approach to design. They're fighting a different war than we are. The mathematics was becoming inescapable. On August 18, 1943, Bauer received a response to his request for American production intelligence. The report, compiled by the Abwehr's Economic Analysis section, arrived in a sealed envelope marked Secret Officer Access Only. The first page showed American tank production for the first 6 months of 1943. Bauer's eyes went straight to the total, nearly 14,000 armored vehicles, in half a year. He pulled out German production records and laid them beside the American estimates. The pages told a story in stark contrast. Germany had built fewer than 4,000 tanks in the same period. For every German tank rolling off the production line, 4 American tanks were being completed. Bauer turned the page, hoping the numbers would level off. They didn't. The projections showed American production accelerating, 3,000 tanks per month by year's end. He did the mental calculation. In a single month, American factories would produce nearly as many tanks as Germany had built in 6 months. He moved deeper into the report, into the sections on engines and raw materials. The numbers there were even more disturbing. The Americans were producing more engines for Sherman tanks alone than Germany was building for all its aircraft and tanks combined. Every month, thousands of Continental radial engines, the same engine sitting in that transmission assembly downstairs, rolled out of American factories while German production struggled to reach a few hundred. Then came the foundation of any industrial war: steel, aluminum, oil. Bauer read the steel production figures. America was producing nearly 3 times more steel than Germany. Aluminum, critical for aircraft and now, apparently, for die-cast transmission housings, nearly 4 times more. But the oil numbers stopped him cold. The United States was producing 23 times more oil than Germany, including all of Germany's synthetic fuel plants combined. 23 to 1. He set down the report and stared at his office wall. Every Sherman he'd examined burned through fuel at rates that would cripple German logistics. But for the Americans, fuel wasn't a constraint. It was abundant. They could afford inefficiency because they had oceans of oil. Germany was fighting an industrial war with workshop tools, while America had deployed factory assembly lines that operated like natural forces, vast, relentless, and completely beyond Germany's ability to match. The transmission downstairs wasn't just a component. It was a symbol of an industrial machine so powerful that German planners had never imagined it existed, and it was just getting started. That last number made Bauer close the report and walk to his office window. 23 to 1. The United States was producing 23 times more oil than Germany. Every Sherman tank he'd examined ran on gasoline. The Continental engine consumed approximately 500 liters per 100 kilometers, inefficient by German standards, but efficiency didn't matter when fuel was abundant. German tanks were increasingly running on synthetic fuel derived from coal because petroleum imports had been cut off. The synthetic fuel production was expensive, energy-intensive, and couldn't possibly scale to match demand. The numbers showed American military production employed over 11 million workers in weapons manufacturing alone. Germany's entire industrial economy, covering everything from tanks to textiles to food processing, employed 14 million. Bauer pictured it. American factories the size of small cities, filled with workers who did nothing but build Shermans, aircraft, ships. Meanwhile, German factories were increasingly staffed by forced laborers who had no investment in quality, no expertise, no reason to care if a transmission lasted 500 kilometers or 5,000. He'd seen the results firsthand. German production quality was declining. American production quality, if this transmission was any indication, was not. Then came the final section, the one he'd been avoiding. Projected totals by the end of 1944. Bauer read the American estimates first. 45,000 Sherman tanks. Just Shermans, not counting other armored vehicles. 96,000 aircraft, 70 aircraft carriers, and hundreds of destroyers. He forced himself to read the German projections. Maybe 10,000 tanks total if everything went perfectly. Perhaps 40,000 aircraft. No carriers. The surface fleet was frozen. Only submarines, which were being sunk faster than they could be replaced. Bauer sat back in his chair and stared at the ceiling. 45,000 Shermans. Each one with a transmission designed to last 8,000 kilometers. Each one backed by fuel supplies that seemed infinite. Each one supported by a logistics system that could deliver spare parts anywhere in the world. He picked up his pencil and began calculating in the margin of the report. Numbers he knew would never appear in any official document. If the Americans built 45,000 tanks, each capable of 8,000 kilometers of operation, that was 360 million kilometers of mobile armored combat power. Even if half never saw combat, even if losses were catastrophic, they'd still have operational capacity that Germany couldn't begin to match. German tanks, even in the best case, would total perhaps 10,000 units with transmission lives averaging 1,000 kilometers. 10 million kilometers of operational capacity. The Americans would have more than 30 times the endurance. And that was just tanks. The aircraft ratios told the same story. The naval comparison was beyond discussion. America was building fleets while Germany built submarines to hide from those fleets. Bauer set down his pencil. The war wasn't being fought on battlefields. It was being fought in factories, and Germany had already lost that battle. The transmission sitting in the workshop below wasn't just evidence, it was prophecy. He began writing his formal report. If American Sherman production reached 45,000 units by end of 1944, and each Sherman had a transmission with an 8,000-kilometer service life, that meant 360 million kilometers of operational capability. German production of 10,000 tanks, with transmission service lives averaging 1,000 kilometers, meant 10 million kilometers of operational capability. The Americans would have 36 times more operational vehicle kilometers available. Even accounting for combat losses, maintenance delays, and logistics, even if half the American tanks never reached combat, they would still have 18 times the operational capability. And that was just tanks. The aircraft ratios were similar. The naval ratios were even more lopsided. Bauer sat at his desk and drafted a single sentence in his notebook. "We are not fighting a nation. We are fighting an industrial phenomenon that produces more war material in a month than we can produce in a year, and they are building equipment more reliable than ours." He stared at that sentence for 20 minutes. Then he began writing his formal report. The numbers Hauptmann Bauer was seeing were staggering, and they painted an undeniable picture. If you're enjoying this deep dive into the industrial side of WWII, make sure you're subscribed to the channel. We release new technical analysis videos every week. And drop a comment. What aspect of WWII history fascinates you most? The technology? The strategy? The human stories? I read every comment. Bauer spent 3 days writing his formal evaluation report. He structured it carefully, opening with technical specifications and measurements, data that no one could dispute. Transmission weight, component counts, wear analysis, metallurgical test results, 17 pages of factual engineering assessment. Then came the section that would define his report's reception. Conclusions and strategic implications. The M4 Sherman transmission represents a fundamental departure from German design philosophy. Where German engineering prioritizes performance maximization through complex, highly tuned systems, American engineering prioritizes reliability and manufacturability through simplified, integrated designs. The Sherman's drivetrain demonstrates no performance compromises relative to German equivalents, while achieving superior reliability, reduced weight, and dramatically reduced manufacturing complexity. Most significantly, the transmission's die-cast aluminum housing indicates a manufacturing capability that German industry cannot currently match. The Americans have solved engineering problems in high-volume precision manufacturing that we have not attempted. Combined with intelligence estimates of American production capacity, this technical assessment leads to an unavoidable conclusion. The United States possesses both the design capability and industrial capacity to produce reliable armored vehicles at a rate approximately 4.1 relative to German production. This disparity is not temporary. It reflects fundamental differences in industrial organization and manufacturing philosophy. The American approach, designing equipment specifically for rapid, high-volume production, is inherently more scalable than the German approach of precision-crafted, performance-optimized equipment requiring extensive skilled labor. Recommendation: German tank development must pivot toward designs optimized for manufacturability rather than performance maximization. Current designs, Panther, Tiger, require excessive manufacturing hours relative to operational lifespan. American designs demonstrate that reliability and ease of production can be achieved without performance sacrifice. Without fundamental changes to design philosophy and manufacturing processes, Germany cannot achieve parity with American AFV production capacity. He read it through twice. Every sentence was defensible. Every conclusion was supported by data. He was reporting objective engineering reality. He was also writing something that contradicted the fundamental narrative driving German military production, that German engineering superiority would counterbalance Allied numerical advantages. Bauer called Richter into his office. "Read this." Tell me if I've overstated anything." Richter spent 15 minutes reading through the report. When he looked up, his expression was grave. "It's accurate," Richter said. "Every word. But Herr Hauptmann—" "I know," Bauer interrupted. "Send it anyway. Through proper channels. Market priority technical intelligence." The report went to the Heereswaffenamt, Army Ordnance Office, on August 25, 1943. The response came 3 weeks later. Not a technical evaluation, not a request for additional data, not a meeting to discuss implications. Instead, a single-page memorandum from an administrative officer. Report filed. Assessment considered excessively pessimistic. Recommend future evaluations. Focus on tactical exploitation of enemy equipment weaknesses rather than capabilities. American mass production methods achieve quantity at expense of quality. Captured equipment may not be representative of average American production. Continue technical analysis of captured material with emphasis on vulnerability assessment. Bauer read the memorandum 3 times. They'd dismissed his data as excessively pessimistic. They'd suggested the multiple Sherman transmissions he'd examined weren't representative. They'd asserted that American mass production meant low quality, despite his 17 pages of measurements proving otherwise. He'd provided evidence. They'd responded with ideology. "They don't want to know," Richter said quietly, reading over Bauer's shoulder. "Or they know, and they can't accept it." Bauer walked to the proving ground window and looked out at the testing track. Another Panther was undergoing trials, its engine roaring. Beautiful machine, powerful, sophisticated, expensive, and absolutely insufficient in the face of what he'd seen. "File the report in our records," Bauer instructed. "Complete copy, and continue the evaluations. When they ask later why we didn't warn them, I want the documentation." "You think they'll ask later?" Richter said. "When American tanks are rolling through Berlin in numbers that seem impossible," Bauer replied, "someone will want to know if anyone saw it coming. And I want to be able to hand them this report and say, yes, we saw it, we measured it, we documented it, and we told you." Over the following months, as more Sherman tanks were captured and evaluated, Bauer filed additional technical reports. Each one documented the same pattern: reliable, well-designed, mass-produced equipment appearing in ever-increasing numbers. Each report was filed and forgotten. November 1943, 3 months after the initial report, the first confirmations arrived from the Eastern Front. Soviet forces were fielding American-supplied M4A2 Sherman's, diesel-engined variants specifically built for Lend-Lease. German tank commanders reported the same characteristics Bauer had documented: reliable, numerous, appearing in formations of 40 to 50 tanks at a time. Combat reports noted that Sherman units maintained higher operational readiness rates than German units. While German Panther battalions typically fielded 50 to 60% of their authorized strength due to mechanical breakdowns, Sherman units maintained 80–85% readiness. The numbers Bauer had predicted were proving conservative. January 1944. Intelligence reports from the Italian front documented American tank employment in exactly the pattern Bauer had warned about. U.S. armored divisions were using their numerical advantage to conduct sustained operations that German units couldn't match. When German tanks broke down, which they did with increasing frequency, there were no replacements. When American tanks were disabled, new ones arrived within days. A captured American maintenance officer, interrogated at Kummersdorf, confirmed what Bauer had discovered through engineering analysis: Sherman transmission replacement time in field conditions, 4 to 6 hours. German transmission replacement on a Panther, 14–18 hours, and that assumed replacement transmissions were available. "We can fix 3 tanks in the time you can fix 1, the American officer had said matter-of-factly, "and we have more tanks to begin with." April 1944. Bauer examined his 7th Sherman transmission, this one from a tank captured in Italy, with an estimated 2,100 kilometers of use. The wear patterns were consistent with all previous examinations, minimal. The gear teeth showed the characteristic light polishing of normal use, but no significant damage. The bearings were within original specifications. Meanwhile, German production reports told a different story. Panther production was achieving 315 units monthly, but operational readiness rates in combat units averaged 37%. The primary failure mode: transmission and final drive breakdowns. Tiger production had peaked at 104 units monthly, but was declining due to manufacturing complexity and resource shortages. Operational readiness, 45–50%, again with drivetrain reliability as the primary limiting factor. The Americans were now producing an estimated 2,000 Sherman's monthly. Even with their longer supply lines and combat losses, the numerical disparity was overwhelming. June 1944, D-Day. Allied forces landed in Normandy with 2,395 tanks in the initial assault force, predominantly Sherman's. Within 3 weeks, over 4,000 additional tanks arrived through the Mulberry harbors and captured ports. German forces in Normandy, facing this onslaught, had approximately 500 operational tanks. The ratio Bauer had calculated 15 months earlier, 4:1 in favor of American production, was playing out in real time on the battlefield. But the reality was worse than simple numbers. The German tanks were technically superior in firepower and armor, but they couldn't be everywhere. The Sherman's could. A German Panther could destroy 3 or 4 Sherman's in a favorable engagement. But there were always 5 more Sherman's, and the Panther had a 40% chance of mechanical breakdown before the next engagement. September 1944. Bauer received a new Sherman transmission for evaluation, this one captured in France. Estimated usage, 3,200 kilometers. The transmission showed more wear than previous examples. It had clearly been through sustained combat operations, but it was still fully functional. No failed components, no urgent repairs needed. He wrote in his evaluation notes, "This transmission has exceeded the operational lifespan of 3 German transmissions and remains serviceable." American maintenance manuals indicate it would be replaced at 8,000 kilometers as preventive maintenance, not due to failure. That same week, German production reports crossed his desk. Total tank production for September 1944, 782 units, all models. Estimated American production, 2,100 Sherman's alone, plus 800 other AFVs. The gap had widened. December 1944. Intelligence reports documented American armored forces advancing across France into Germany itself. Entire U.S. armored divisions with 250-plus tanks each. Multiple divisions. The numbers that had seemed impossible in 1943 were now reality. German tank production was collapsing. Allied bombing had damaged critical component factories. Resource shortages meant transmission manufacturers couldn't get required materials. The Panther and Tiger designs, so sophisticated and powerful, required materials and manufacturing time that no longer existed. Meanwhile, American Sherman production continued unabated. The factories Bauer had read about in intelligence reports, Ford's Willow Run, Chrysler's Tank Arsenal, General Motors' converted automobile plants, were still running at full capacity. The prophecy documented in his August 1943 report had been fulfilled in every detail, and it was far too late to change course. May 1945. Kummersdorf proving grounds, occupied by Soviet forces. When the archives were finally opened after the war, the complete picture emerged, and it was even more staggering than Bauer had calculated in 1943. The Americans had built nearly 50,000 Sherman tanks. At peak production in May 1944, they were completing 1 Sherman every 11 minutes, around the clock. It took German factories 5 times longer to build a Panther than it took American factories to build a Sherman, and the Sherman's transmission lasted longer. Germany had produced roughly 16,000 tanks of all types combined. 3 Shermans for every German tank. But the real advantage was hidden in the manufacturing time. The Americans weren't just building more tanks faster, they were doing it with a fraction of the labor hours per vehicle. But the transmission Bauer had examined in July 1943 was only the beginning. That single component had hinted at an industrial capacity that intelligence analysts struggled to believe even as they documented it. The complete accounting told a story almost beyond comprehension. America built nearly 300,000 aircraft. Germany built 119,000. America built 86,000 tanks. Germany built 46,000. But most German tanks had shorter operational lives and required more maintenance. America built 2 million trucks. Germany built barely a third of that and relied increasingly on horses as vehicle production failed to keep pace with losses. And then there was the naval comparison, one that rendered any discussion of parity meaningless. America launched thousands of ships, including hundreds of major combat vessels. Germany, with its surface fleet in ruins, built submarines to hide from the fleets it could never challenge. The transmission sitting on that workbench in Kummersdorf in July 1943 had been an artifact from a different kind of civilization, one that had solved problems German industry hadn't known needed solving, one that designed for production scale as naturally as German engineers designed for performance. Bauer had measured one component and seen the war's outcome written in aluminum and steel. The final numbers merely confirmed what that transmission had already revealed. Germany was fighting an industrial giant with the tools of a craftsman's workshop. The arithmetic had been brutal. The reality was even more so. June 1945. Allied Interrogation Center, Wiesbaden. Hauptmann Ernst Bauer, now a prisoner of war, sat across from an American technical intelligence officer. The American had Bauer's August 1943 report on the table. "This is remarkably accurate," the American said. "Your production estimates were actually conservative. We built more than you predicted." "I know," Bauer replied in careful English. "I saw the results. In Normandy. In the Ardennes. Here." "Why wasn't this report acted on?" Bauer considered the question. "Because it contradicted what leadership wanted to believe. German engineering was supposed to be superior. Quality was supposed to overcome quantity. The idea that America could build better equipment faster, that wasn't acceptable." The American made notes. "What happened to your report?" "Filed and forgotten. I submitted 3 follow-up evaluations over the next year. Same data, same conclusions. All filed. And the transmissions? Your analysis of our manufacturing methods? All confirmed. Every captured Sherman we examined told the same story. Reliable, well-designed, mass-produced without quality compromise." Bauer paused. "You won the war in your factories. We lost it in ours." The interrogator pulled out a document. "This is interesting. Your report was found in the archives with a notation, defeatist assessment. Author may require ideological re-education." "Did that happen?" "No, I was too useful. They needed engineers who could evaluate captured equipment, even if they didn't like what we found." The American closed his folder. "Your report will be included in our technical intelligence archives. It's one of the few German assessments that accurately understood American industrial capability." Bauer nodded. "Understanding doesn't matter if no one listens." The historical record proved Hauptmann Bauer right in every detail. If this kind of detailed technical history interests you, you'll love our other videos analyzing WWII equipment and strategy. Check out the playlist in the description. And before we wrap up with the bigger lesson here, hit that like button if you appreciate this level of research and detail in history content. The story of Ernst Bauer and the Sherman transmission is a microcosm of a larger pattern that repeated throughout the war. Competent technical experts recognized reality, and the system that employed them ignored it. Bauer wasn't alone. German engineers and intelligence officers filed similar reports across multiple domains. Luftwaffe technical officers documented American fighter aircraft production in 1942, predicting overwhelming Allied air superiority by 1944. Their reports were dismissed as defeatist. Naval intelligence calculated American shipbuilding capacity in 1941, warning that U-boat warfare could not win an attrition battle against American production. Admiral Dönitz rejected the analysis. Economic planners documented German oil shortages and calculated that synthetic fuel production could never meet military demands. Their recommendations for strategic defensive posture were overruled. Signals intelligence experts broke American convoy codes and warned that Allied logistics capacity far exceeded German estimates. The intelligence was ignored in favor of optimistic assessments. The pattern was consistent. When objective analysis contradicted the fundamental assumptions driving strategy, the analysis was rejected. Why? Because the German war effort was built on an ideological foundation. German technical superiority, fighting spirit, and will would overcome Allied material advantages. Accepting data that contradicted this foundation meant accepting that the war was unwinnable, and that conclusion was literally unthinkable within the system. Bauer's transmission report documented this in engineering terms. The Americans hadn't just outproduced Germany, they'd out-engineered Germany in the dimension that mattered most, manufacturing efficiency. They designed equipment that was reliable, effective, and optimized for the industrial war they were fighting. German engineering, for all its sophistication, was optimized for a war of quality versus quantity, a war where superior performance per unit would compensate for numerical inferiority. But the Allies weren't offering that war. They were offering quantity with quality, and they were doing it faster than German intelligence had believed possible. The arithmetic was brutal and unavoidable. Bauer had calculated it in August 1943. Others had calculated similar numbers in other domains. The conclusions were always the same. Germany could not win a prolonged industrial war against the Allied coalition. But arithmetic requires accepting uncomfortable truths. It requires acknowledging when assumptions are wrong. It requires the intellectual humility to change course based on evidence. The Sherman transmission represented evidence, 17 pages of measurements, metallurgical analysis, manufacturing assessment, and production mathematics, all ignored because it contradicted ideology. By the time reality forced acknowledgement, it was far too late. The factories Bauer had read about in 1943 had produced tens of thousands of tanks. The transmission that had revealed the truth in miniature had been replicated 49,234 times. The war of production had been lost before most German leaders admitted it was being fought. In the end, Hauptmann Bauer's first instinct, standing beside that Sherman on July 23, 1943, had been correct. The transmission in front of him explained why Germany couldn't win. The numbers proved it. Reality confirmed it. All that remained was for leadership to accept it. And by then, acceptance no longer mattered. Thank you for watching this deep dive into one of WWII's most revealing technical discoveries. The story of Hauptmann Ernst Bauer reminds us that objective engineering analysis matters, even when, especially when, it contradicts prevailing assumptions. There's another fascinating technical analysis video appearing on your screen right now, exploring American industrial innovation during WWII. If you enjoyed this level of historical detail and technical depth, you'll find that analysis equally compelling. I'll see you in the next one.